Got a 2-gram sample of peanut butter. It's placed into a bomb calorimeter, right? And charged with excess oxygen, placed into 2 liters of water, which is at 23.75 degrees Celsius. Previously, the constant for the calorimeter was determined to be 3.125 kilojoules per degree Celsius. After the peanut butter sample was ignited, the water temperature rose to 28.213 degrees Celsius. Determine the number of calories in one serving, 32 grams or 31 grams of peanut butter. Given that one dietary calorie, food calorie, is 4,184 joules. So yeah, all we really have to do is just find the energy released from the 2 grams of the peanut butter. And then once we get that, we're just going to do a conversion, basically saying, okay, I don't have 2 grams anymore. I have 31 grams. So we're going to multiply that to give us the overall energy in 31 grams. All right, so we got 2 steps. We got to find the heat from the water and the heat from the calorimeter, right? So we'll do Q of the water, right, equals MC delta T. And my heat that the water absorbs, I have 2 liters of water, and I know that 1 liter is 1,000 milliliters, and I know that 1 milliliter is 1 gram, right? So I've got 2,000 grams of water. The heat capacity of the specific heat of water is 4.184 joules, grams, degrees Celsius. And then my delta T of the water, I go from 23 to 28. So 28.213 minus 23.75, right, 4.463 degrees Celsius. So the heat that the water absorbs, so whatever that is, 2,000 times 4.184 times that, right, 37,300, and transpose those numbers, 346. And then we also want to find the energy that the calorimeter absorbs. So the calorimeter would go through the same temperature change, and the heat capacity of the calorimeter is 3.125 kilojoules per degree Celsius. So for this, we need Q equals C delta T, where Q is the calorimeter, C is this 3.125 kilojoules per degree Celsius, and my delta T is going to be the same delta T right here, so 4.463. So Q, the calorimeter, 4.463 times 3.125 is, and just be careful with units, 13.9, we'll say 4.6, right, kilojoules. So I have joules here, I have kilojoules here. I need to find the total energy that was released from burning the combustion of the peanut butter. So I'm going to convert the water into kilojoules, the water energy into kilojoules.
Dr. French?
Yeah.
Yeah, if we were given, like, let's say we put the right sig figs, right, but Top Hat marks it wrong, could we still get like points for it, even though
You're
the
still getting points for it. You get participation credit for it.
No, I mean for the actual exam.
You're gonna get it'll have the same setting where you will get partial credit for having the correct significant figures, or sorry, the correct answer but the wrong significant figures.
Yeah, because in the other question, you said it's 1.1 and then like 3 sig figs, but Top Hat takes it as 2 sig figs.
I said it was 1 point. I said it should be. I changed. Top Hat wanted 3 significant figures originally. 1.1 or sorry. Top Hat wants it as 2 significant figures, 1.1, right? And that's what I said the answer was 1.1. But I said other people had thought that it was 3 significant figures. And so I said it was kind of a tricky answer that way.
Why would it be 2 sig figs though, if the smallest sig fig in the question is 3 sig figs?
Yeah, and I think they're getting it from the delta T, the change in temperature from the change in temperature between the two is 9.2 degrees. So that's the only thing I can think of that they're getting it from the 2 significant figures from.
Okay,
Is
thank
from
you.
that change in temperature. So for the combustion reaction, we have to add these 2 energies together to get the total energy, and then we're going to relate that to, that came from 2 grams of peanut butter. So I want to convert, I guess what I was like, yeah, I was converting the energy of the water into kilojoules, right? So the water was 37,346.38 joules, right? I know 1,000 joules, 1 kilojoule, divide by 1,000. I get 37.346
So it's like, because normally we'd be playing on grass where if you use cleats,
kilojoules. All right, so
you're running at full speed and
I
playing
want
just
Q overall
an inch or two.
So 13.94 plus 37.346. Add those kilojoules together.
Saying with like, just saying, I think I was on defaults. So I was trying to follow
37.346. Yeah, I don't have time to find them right now and mute it.
They tried to fake me out going like that and then running that way or something. And then
Diego, mute your mic.
All right, we've got 51 kilojoules that are released, and that came from the 2 gram sample of water. So 2 things, we need to get this into units of calories. And so, okay, 2 grams of peanut butter, right, gave off 51.29 kilojoules of energy. So let's put that into calories and then compare that to 31 grams. So I know that we got 51.29 kilojoules. I know that in 1 capital C calorie, there's 4.184 kilojoules. So all I did was just convert that in my head from joules to kilojoules. That'll give me calories, food calories. So divide that by 4.184. I get 12.259 calories, and that was per 2 grams of peanut butter, right? So, okay, I've got 12. Let's see, I've got 31 grams of peanut butter, and I want to find out how much energy that is. Well, my conversion factor is for every 2 grams of peanut butter, I'm going to have 12.259 calories. So that grams should cancel out and leave me with calories in 31 grams or 2 tablespoons of peanut butter. So 31 times divided by 2. All right, I get about 190 calories. So it should be 3 significant figures because the 2 gram sample is 3 significant figures. Everything else has more than that, right? I've got 5 significant figures, but I would be limited by the 2 grams is 3 significant figures. So I would say 1.90 e to the 2 calories, right? Yeah, good question, Tiffany. Why did we convert the joules into kilojoules? I should have converted it into joules. You're right. For some reason, I converted it into kilojoules. And then after I did that, I looked up and saw that they defined 1 calorie in joules. So I should have calculated it, converted them both into joules. And then that way I wouldn't have had to convert the 1 calorie into kilojoules. I just didn't realize it at the time. And then, yeah, so we have 2 things. You've got the bomb calorimeter itself and the water. So the water goes up in temperature from 23 to 28 degrees, and the bomb calorimeter itself also. So it equilibrates at 23 degrees. So the whole thing, the calorimeter and the water, are equilibrated. You go through this process of burning the peanut butter, and both of those, the calorimeter and the water, go through that temperature change. So that's why we had to calculate it for the water and for the calorimeter. And so how do I know to do a 2-step and only calculate the Q for the calorimeter? Right, we want to calculate, I mean, the calorimeter is within the water. They give us the temperature change of the water. They give us the heat capacity of the calorimeter. So given that information, both of those things are going through that temperature change. It's not 100% clear probably, but because in most of the times we've done these calculations, we've either just looked at the heat capacity of the whole thing. They tell us the heat capacity for the calorimeter, but we have to also take into account that the water as well. The water is also undergoing a temperature change. So yeah, question 19 is a little bit more involved. All right, what would we have next? Oh, okay, yeah. We had to add, I know it's a little bit sloppy. I kind of ran out of space and didn't do a good job. We had to add those energies together. The Q from the calorimeter and the Q from the water, we had to add those together to find the overall energy that was released from the peanut butter, because the water went through a temperature change, the calorimeter went through a temperature change. So because both of those things were absorbing energy, we had to find the total energy and add those 2 values together.